Hello, everyone. I uh, we have a problem today that's coming from this website I maintain. So let's mm, it's an interesting problem in a stress strain chapter. I'm doing from this book. I'm doing chapter by chapter, and we are now on the stress and strain chapter. And this is an interesting problem in that chapter. In that chapter, we only this problem only does stress at this location, but I thought maybe I would just strain also. So I looked up Young modulus of say a pretty strong wood like walnut wood, and so we'll work it out. I don't know what the numbers will look like offhand, so let's start with some always just draw something to get your mind into the problem, right? It's always a good idea to draw the so let's draw it out. And so here is a table. Here is a table, okay, and it's got these legs. This pretty heavy table, and then on top of the table sits table has this would also has some thickness, and on top of the table sits some big machine. You can, so there is this area of contact is A, and this area of contact, each of those legs is A here, little a here, and little a here, and little a here. So you can see the different parts of wood have a different stress, right? Say I want to do A first. If I do A first, then I will go right under the machine. I will ask a question: what's happening in this tiny space? Okay, so here is a wood. Let me redraw it. So I have a tiny space wood like this. On this wood, you have the weight of the machine. So weight of machine. And if there was only force on that piece of the wood, so this is a infinitesimal element of table. Like this is, say, delta z or something, and delta z, I'm thinking, go to 0, and this area is a big A, capital A. So this is there's another, you can say there is a weight of this guy itself is acting on this weight of the delta weight of this surface. But when delta z goes to 0, this goes to 0. So there's a net force on this, and it should be accelerating. So there must be something wrong with this idea, right? And net force is which just means there is some other force, and the acceleration of this guy is acceleration is 0, which means from F equals ma there is another force, and that is where the stress is coming from. So this is from the rest of the table, like other parts of the table. So the table is table is yay thick underneath here. So this is this is the table. So the table is this surface. So this is part of the surface of the table, and the table, and all these are table. All these are table, and legs are here. Legs are here. Okay, legs are those guys. So these are thickness of the table, and so rest this piece of the table is actually must be matching this force. So what is this force? This is stress. If the stress was sigma here, then this force will be sigma times the area of contact. Okay, so that's how we know sigma times area equals to the weight of the machine, which is capital mg. So sigma is mg over capital A. Okay, A is given to be 1000 centimeters square, and 1 centimeter is 10 to the minus 2 meter. So 1 centimeter square is 1 centimeter by 1 centimeter. So there are two of them, right? So this will be 10 to the minus 2, this will 10 to the minus 2, this will be 10 to the power minus 4 meter square. This is a very common place people make a mistake. So when put it in here, it's 0.1 meter square. So m is 2000 kilogram, and g is 10 meter per second square. I'm going to take a 10, it is 9.8 just for simplicity, and this is 0.1 meter square. So when I work this out, 1 2 3 4 and then 5 zeros, so 2 times 10 to the power 5 Pascal. I got a Newton over meter square, which is same as Pascal, because that's the answer for the stress. Now to the strain. Strain, what will be the strain? So strain, so we already know the stress. So strain is, say, epsilon. So sigma should be Young's modulus, because this is compression here, Young's modulus times epsilon. And Young's modulus is given there, so the epsilon is sigma over y. So sigma is this 2 times 10 to the power 5 Pascal, and this thing is given gigapascal, which is 10 to the power 9. So 10 to the power 10 here, so 10 to the power 10 Pascal. So this is 2 times 10 to the minus 5, and you can see the Pascal cancelled out, and so strain is just in terms of just a unitless. So if you had a say if the table was, if this was a 2 centimeter thick, then it will be the amount of compression will be 2 times say 1 centimeter thick, maybe 1 inch, let's call it 1 inch thick. This is going to 2 times 10 to the power minus 5 inch. It's going to be dipped by that much. Okay, so that's what this means, the ratio of how much that got dipped to how thick it was. All right, how about part B? Okay, so part B, we're going to look at this one of the legs, right? We look at one of the legs, because all 4 legs are in similar situation. So let's look at just in a little bit expanded view. So this is one of the legs, and this is where the floor is. So on this, we again look at a infinitesimal element of this. So on that element, let's look at a separate way. Okay, so this is the element. So what are the forces on it? Well, there is a from the floor, this is the normal force from the floor on this leg, and then there is a force from the other part of the table. So this part of the table, the stress stress in this part of the table, and that stress was some new sigma times this new area. This area is, say, little a, and so, and but the acceleration of this little piece that we wrote down here, acceleration is 0, so these forces must balance out, right? We just need to know what to use for n, because we already know a. This has to be equal to that. So what is the n we have to use? Well, looking at this, the weight of this machine and the weight of the entire table will be on 4 legs. So this n will equal, n should equals 1/4 of m plus mg, because the acceleration is 0. So we already can say this must be equal to that. The entire table, everything, if I think of all this as one system and acceleration is 0, then on this whole system you have m plus mg, and then you have a normal from the 4 legs, 4 times the normal, each one being m, and so this has to be equal to that, and that gives me that. Okay, I equate this, so sigma a equals to 1/4 m plus mg, and so sigma is 1/4a m plus mg. Now we have 20 centimeters, so 1/4 times 20 times 10 to the power minus 4. Remember, centimeter square has to be converted to meter square. And m plus m is 2,200 kilogram times 10. So that's so let's see what do we have. We have 0 cancels 0, and so let's write down 22/8, and you have 10 to the power 2 here, plus 2 is 6, and this whole thing should turn out to be Pascal. So 2.8 or 9, something like that, 10 to the power 6 Pascal. Okay, so something like that, very close to that. Okay, so we got the sigma. How do I get what's the strain here? I mean, like, how much leg has changed, how much strain is here. So strain is just Hooke's law again. So strain will become sigma y equals to y epsilon equals sigma, so epsilon equal to sigma over y, and because it is compressed, so it's using Hooke's law for that goes with a change in length. So this stands for delta L over L, and sigma over y is 2.8 times 10 to the power 6 over, we have a 10 times 10 to the power 9. So this is Pascal and this is Pascal. So we have 2.8 times 10 to the power minus 4. So actually over here per inch, so this means 2.8 times 10 to the power minus 4 inch per inch of table leg. That's how much it's gonna compress. Okay, I'm gonna stop here. The next important concept to cover in this chapter is the energy. How much energy is stored? So when these guys are compressed around here, they're storing energy. Okay, so we're going to talk about energy in my next video. Now if you like this kind of video, definitely put a like button, and if you subscribe, it makes the circulation go up, and hopefully more people will be able to learn from these videos. Okay, talk to you later. Bye.